Good evening, everyone. Welcome to this course on hydraulic engineering, week 3 content. So, this week's content is basically based on laminar and turbulent flow through pipes. So, before we start with the practice problems, I would like to discuss some important aspects that are associated with laminar flow through pipes and turbulent flow through pipes, because majority of the problems in today's sessions is based on laminar and turbulent flow in pipes. Now, to begin with, the first important concept is the concept of Reynolds number. Whenever we consider pipe flow, now what is a pipe flow? When there is a pipe which is flowing full. When this pipe is flowing full, this is the longitudinal section of a pipe which is flowing full. Now, this entire pipe is flowing full with some particular fluid, then we call it a pipe flow, the case of a pipe flow. Now, there are two possible cases. One is laminar flow and the other one is turbulent flow. Now, how we can distinguish between laminar and turbulent flow? Now, in order to distinguish between laminar and turbulent flow, we use a non-dimensional factor or number which is known as Reynolds number. What is Reynolds number? Reynolds number, by definition, is the ratio of the inertial force by viscous force. It means that if Reynolds number value is very high, then it means that the impact of inertial force is much higher on the flow in comparison to the viscous force. And when the value of Reynolds number is less, then we say that the impact of viscous forces in the flow system is higher than the impact of the inertial force. Now, inertial force can be written as mass into acceleration. So, mass into some acceleration component. Mass can be written as density into volume into acceleration, or rho volume. Acceleration is nothing but length, sorry, is nothing but some velocity u by time. I'm just writing it dimensionally. So, rho volume is area into some length u by t, or let us keep it like this. Now we have the viscous force. So viscous force, we can get viscous stress tau from Newton's law of viscosity. So what does Newton's law of viscosity give us? Newton's law of viscosity tells us that tau is equal to mu du by dy. So from this, tau is the shear stress. So dimensionally I can write this as mu. Du is basically some velocity and dy is some length, u by l, tau mu by l. But if we want viscous force, so viscous force is tau into some area. Okay, so if I write the same thing here, then what will be viscous force? Viscous force Fv will be tau into some area. Okay, now what is tau? Tau is mu u by L into A. Okay, so we have some expression for inertial force, we have some expression for viscous force. Then what will be Reynolds number? Sorry. Reynolds number Re by definition is the ratio of inertial force by viscous force. So inertial force is rho A L U by T divided by viscous force. So I can write it as L divided by mu u A. Now see, this A, sorry, this A and this A cancels out, this U and this U cancel out. Okay, so what we are left with is rho L L by mu T. Now, if we look carefully, this L by T, this L by T is nothing but some velocity. So, we can finally write that Reynolds number is equal to rho U L by mu. So this is the expression for Reynolds number. It is a dimensionless parameter or quantity which signifies ratio of the inertial force to viscous force. Now here rho is the density of the fluid, U is the velocity, a velocity component, mu is the coefficient of dynamic viscosity, and L is the characteristic length scale of the problem. Now what is characteristic length? Characteristics length. Okay, now this characteristic length is basically a length scale which is representative of the system under consideration. For example, if we consider flow through pipe, uh, characteristic length is either the diameter d or the radius r. Okay, they are of the same order of magnitude, so we either use d or r. However, the common convention is to use the diameter d of the pipe. Then in open channel flow, we can use the ratio of weighted area by weighted perimeter, which is the hydraulic mean depth, as the characteristic length. Sometimes uh, the ratio A by T is used as the characteristic length, or sometimes the top width T is taken as the characteristic length. So basically it depends upon the system. However, the selection of the characteristic length must be done in such a way that it should represent the system under consideration. It should properly represent the system under consideration. So first of all, uh, again to summarize, we are discussing laminar and turbulent flow through pipes. Now, before solving the problems, we are discussing the basic concepts that are useful in solving the problem. So, the first important concept is the concept of Reynolds number. So, Reynolds number is the ratio of inertial force by viscous force, which basically amounts to rho u L by mu. Okay, and in case of pipe flow, as we have already seen, in case of, sorry, in case of pipe flow, this Reynolds number thus can be written as rho v, that is the average velocity, cross sectional velocity at a particular pipe section, d by mu, where d is the diameter of the pipe. Okay, now why this Reynolds number is important? This Reynolds number is important because it gives us an idea whether the flow is laminar or turbulent. Okay, a very regular type of flow is known as laminar flow, or uh, more like if you would like to understand it more technically, then laminar flow is a flow where the viscous forces dominate the inertial forces. However, in case of turbulent flow, the flow is highly chaotic in nature, irregular, random, and in terms of the inertial and viscous force in turbulent flow, the mm, contribution of the inertial forces is much higher than the contribution of the viscous forces. Okay, the flow is basically dominated by the inertial forces in case of turbulent flow. So, in case of pipe flow, okay, in case of a fully developed pipe flow, if our Reynolds number is less than 2000, then we say that the flow is laminar. We say that the flow is laminar. If Reynolds number is greater than 4000, we say that the flow is turbulent. However, if Reynolds number lies between 2000 to 4000, we say that the flow is in transition. So the flow is in transition from laminar to the turbulent state. So this is the importance of Reynolds number, because for a particular type of flow, Reynolds number tells us whether the flow lies in the laminar regime, turbulent regime, or it is still in transition from laminar to turbulent regime. So this is for Reynolds number. Next is the concept of laminar flow through pipes. Okay, so in order to understand laminar flow through pipes, because the analysis of the laminar flow is the equations, for example the variation of the velocity at a particular section or the maximum velocity, is entirely different for laminar flow through pipes and turbulent flow through pipes. So we will next look into the equations for laminar flow. So for laminar flow, we will consider the case of the flow of, we'll consider the case of flow of a viscous fluid through a pipe. Okay, or it is also known as Hagen-Poiseuille, Hagen-Poiseuille, Poiseuille, Hagen-Poiseuille law. Okay, so first of all, in order to these things must have been covered in the lecture also, but since we will be solving some problem, just in order to revise the theory, uh, my attempt is to redo the, sorry, yeah, my attempt is to redo the calculations. Okay, redo the derivations. So let us consider the flow through a pipe. Okay, flow of a viscous fluid. So say this is the pipe. Okay, and we have considered a particular section of the pipe lying between, say, here to here. Okay, we have considered a particular section of a pipe whose length is, say, L. Okay, now in the, and this is, say, mm, the center line of the pipe. Okay, now say the radius of the pipe, say it is a pipe of uniform diameter, and say the radius of the pipe is R and the diameter of the pipe is, say, D. Okay, so diameter is nothing but twice of the radius. Okay, it's, say, R. Now say this is our section 1 and this is our section 2. The distance between section 1 and section 2 is L, and let us consider a small fluid element. Okay, let us consider a small fluid element which is in the shape of a cylinder. Okay, exactly at the center. Let me change the color. Say we have a fluid element, a cylindrical fluid element. Okay, we have a cylindrical fluid element exactly at the center, such that the radius of this cylindrical fluid element is R. Okay, the radius of this cylindrical fluid element is R, and its length of this fluid element is dx, that is elemental length. Okay, elemental length for this fluid element. Hmm. Now, what are the assumptions? Assumptions behind any derivation. Okay, what are the assumptions? It is very important. Assumption 1, the first assumption is that fluid follows Newton's laws of Newton's law of viscosity. This is our first assumption, and this is quite obvious from the heading also, because we are considering the flow of a viscous fluid. Okay, and the second assumption is no slip condition is valid at the pipe boundary or the pipe wall. Okay, so what is no slip boundary condition? We have already discussed the no slip boundary condition during week 1 of this lecture. So no slip boundary condition basically means that the relative velocity between the fluid particles which are in contact with the solid surface and the solid surface is zero. So since the pipe wall is fixed, the fluid particles which are in contact with the pipe wall are also having zero velocity. Okay, so these are the assumptions. Now let the pressure forces, okay, the forces that are acting on the third assumption. What are the forces that are acting on this system that we'll be considering? One is the pressure force, okay, and the other one is the shear force. Okay, shear force between the fluid and the pipe wall, and the pressure force on the fluid element. Okay, now the derivation approach that we'll be following here is basically the equilibrium of forces, or we'll try to solve it by Newton's second law of motion. Okay, the fundamental equation that we'll be using is the Newton's second law of motion, or Newton's second law of, or conservation of linear momentum. So if we apply conservation of linear momentum, then yeah, yeah. For this fluid element, okay, so for this fluid element, if this is the flow direction, say the flow direction in the pipe is this. So for this flow direction, the shear stress will be acting in a direction opposite to the flow. Okay, tau. This will be the direction of tau. The pressure force here on this face, say the pressure force denoted by P is P I R square. Okay, because pi, for this small cylindrical element the radius is R, so the cross sectional area will be pi R square, and the pressure force that is acting is P pi R square. Okay, P pi R square. Now what will be the pressure force on this face, on the other end? On the other end, the pressure force, if we use linear variation of pressure and following Taylor's series expansion, pressure will be P plus del P by del X into dx into pi r square. So basically what is the idea? The idea is the pressure on this particular face is given by P pi r square. The pressure on this particular face is given by the pressure on this particular face is given by P plus del P by del X dx. This is the pressure into pi r square. But what is the direction on the fluid element? So the direction on the fluid element is this particular pressure P pi r square, which is acting on this face, is along this direction. Okay, that is the positive x-axis, say, and the pressure which is acting on the other side will be along the negative x-axis. Okay, what about the shear stress tau, or what will be the shear force? First of all, what will be the shear force that is acting on this fluid element? The shear force acting on this fluid element will be tau, that is the shear stress multiplied with the area. But what will be the area? The shear stress is acting on, okay, let us consider a case. Say say this is a paper. Okay, say this is a paper, a rectangular sheet of paper, and after rolling the paper you have made a cylinder. Okay, you have made a cylinder. Now the shear force is acting on the curved surface of this cylinder. So if you open this paper, then again you will be getting this rectangle. So basically the shear force is acting on this area. Okay, so following the same idea, there is a cylinder whose radius is r. Okay, now if you open up this paper, then what will be this dimension? This dimension will be 2 pi r, that is the circumference of the cylinder. Means if you open up, you will be getting a rectangle such that one of the dimension of the rectangle is 2 pi r and the other dimension is basically the length of the cylinder. So in this case it is dx. Okay, so if this is the case, then tau will be multiplied with the area. So area will be 2 pi r. Okay, 2 pi r into dx. Okay, and what is the direction? It is acting along this direction. So now we have three forces acting in this system. We have three forces. What are these three forces? These three forces are: one is the pressure force which is acting along the positive x-axis, one is the pressure force which is acting along the negative x-axis, and one is the shear stress which is acting along the negative x-axis or in the direction opposite to the direction of flow. So now if along x-axis, if we write the force equilibrium equation, then what will be the force equilibrium equation? The summation of the pressure, so P pi r square minus P plus del P by del x dx, sorry, into pi r square minus tau into 2 pi r into dx will be equal to 0. Okay, so now if you just do the calculations, what will you get? See, this p pi r square and p pi r square will get cancelled because there is a negative sign. So effectively you will be left with minus of del p by del x into dx pi r square minus of tau 2 pi r dx is equal to 0, or tau into 2 pi r dx is equal to minus of del p by del x dx into pi r square. Now some terms will get cancelled. So what are those terms? Pi and pi will get cancelled. So this pi and this pi will get cancelled. This r and one of the r's will get cancelled. This dx term and this dx term will get cancelled. Okay, so what is there then? Tau is equal to minus of r by 2. Okay, tau is minus of r by 2 into del p by del x. So this is the expression for shear stress. Now here, for a pipe flow, the pressure gradient along the flow direction, that is del p by del x, is a constant. Okay, del p by del x is a constant. This can be proved from Navier-Stokes equation after suitable assumptions which are relevant to viscous and laminar flow through a pipe. Okay, viscous flow through a pipe. Del p by del x is a constant. Okay. However, this equation has many other important features. What are those? Excuse me. Yeah. Hmm. Many other important conclusions which can be drawn from this equation. First of all, the first point is the flow will take place only if there is a pressure gradient, that is del P by del X, along the flow direction. Okay, there is a pressure gradient along flow direction. So pressure gradient along flow direction is del P by del X. So only if del P by del X exists, that is if pressure gradient exists along the flow direction, only in that case flow will take place in case of a pipe. Further, we can see that there is a negative sign. What is the significance of this negative sign? The significance of this negative sign is that pressure is falling or decreasing. Okay, it is decreasing or falling along the flow direction. This is again a very important deduction that can be made from this equation. Okay, so first important part is the flow will take place only if there is a pressure gradient along the flow direction. Second point is the pressure gradient is there in such a way that the pressure is decreasing along the flow direction. Then, as I have told you, that this del P by del X is a constant, and this can be uh, derived from Navier-Stokes equation. Okay, this can be derived from Navier-Stokes equation. So, if you look carefully, this equation is similar to a form tau is equal to minus of mx. Okay, where x is nothing but r. So, what does this indicate? It indicates that shear stress. Okay, it indicates that shear stress varies linearly. Okay, how shear stress vary? Shear stress varies linearly with R. Okay, so at the pipe center value of R is equal to 0, so shear stress is 0. At the pipe wall value of R is equal to R, so shear stress is maximum, so tau max will be getting minus of R by 2 del P by del X. And if you draw a qualitative figure, how it will look like? It will look something like this. So this is the pipe wall, this is the pipe center. If we are drawing the variation of shear stress at a particular section, then at the center it is 0, at the pipe wall it is maximum, and it is varying linearly. Okay, so this is the variation of shear stress tau. Okay, fine. Next, we have seen the variation of shear stress. The first important formula that we have obtained is the variation of shear stress. So for which, for variation of shear stress, excuse me, tau is equal to minus of r by 2 del p by del x. Okay, next is the variation of velocity, that is u. What is the variation of velocity? Just like this at a particular section. So in order to obtain the variation of velocity, we will again refer to the same graph, or sorry, the same problem figure, and we will be using one important property or assumption that we have used. We have considered that the fluid that is flowing in the pipe is a viscous fluid. So if this is a viscous fluid, then it must satisfy Newton's law of viscosity. Mu du by dy means we have assumed that it is a viscous. See, even if it does not follow Newton's law of viscosity, then also it can be a viscous fluid. How? If you remember, the general equation is shear stress versus velocity gradient. It is a plus b du by dy raised to the power n. But if it is a Newtonian fluid, then the value of A is equal to 0 and the value of B is equal to 1. Yeah, sorry, value of B is equal to mu and value of N is equal to 1. So we have considered a Newtonian fluid, okay, which obeys Newton's law of viscosity. It is a viscous fluid which obeys Newton's law of viscosity. Okay. Now, what is y basically? What is y? Y is the distance measured from the pipe wall. Okay, so this is the figure. This is the pipe wall. If this is the pipe center, if say this is the pipe center, small r is measured from the center of the pipe, in that case y, okay, now when you write the Newton's law of viscosity, this y varies from the solid boundary. So in case of this pipe, this is the solid boundary or this is the solid boundary. So if you consider only one half, either the portion below the center line of the pipe or the portion above the center of the pipe, so from the solid portion, this is y. Now what is the relationship between y and small r? See, this total distance is r, capital R. Then if you consider this point, okay, this point is basically what? If you measure from here, it is y, if from the pipe boundary, okay, this is y. So y is basically r minus r from figure. Okay, geometrically we can very easily observe that or very easily write that y is equal to r minus r. Therefore dy will be minus of dr, because r is a constant if we differentiate. Okay, in that case this tau can be written as mu du by, see, instead of dy, what we can write? Du by dr, dr by dy. Okay, chain rule. So tau, what is dr by dy? Minus 1. So minus of mu du by dr. This is the shear stress. Okay. Now we have already seen that tau is equal to minus of r by 2 del p by del x. This we have already derived. So if we compare this equation and this equation, what you can write? We can write that minus mu du by dr is equal to minus of r by 2 del p by del x, or we can write that du by dr is equal to 1 by twice mu del p by del x r. Okay, so this is, we can see that it is a differential equation. What is the order of this differential equation? The order of this differential equation is 1. So it is a first order ordinary differential equation. And here the unknown is u. Okay. Now the variable u, and it is a function of r. So the independent variable is r. So what will be u? So by direct integration, 1 by twice mu del p by del x integration of r dr. Okay, this will be the solution. Or u is equal to 1 by twice mu del p by del x, r dr can be written as r square by 2. So instead of 2 I am writing 4 here. Okay, plus some constant of integration. So finally what we have? We have u is equal to 1 by 4 mu del p by del x plus r, del p del x r square plus some constant of integration. Now see, there are infinite possible combination values of u which will satisfy this. How? Because c is any real constant. Okay, c is any real number. C can be any real number. And on the number line, we can take infinite number of real number, and all those infinite values are possible solution for this. But we need a unique solution. And for a unique solution, what we have? We need a suitable boundary condition. We need a suitable boundary condition. Now, in order to obtain a suitable boundary condition, what condition we can use? We can use the no slip boundary condition. We can use the no slip boundary condition. So what does no slip boundary condition states? That u is equal to 0 when value of y is equal to r. Sorry, not value. U is equal to 0 when the value of r is equal to r. Okay. So if we use the same thing, u will be 0 where when the value of small r will be equal to capital R plus C. So from here value of C is equal to minus of 1 by 4 mu del P by del X R square. And if you use this expression of C in the main equation, what will you get? You will get U is minus of 1 by 4 mu del P by del X R square minus R square. Clear? So this is the variation of velocity u with r. Okay. Now you can see that this variation is parabolic in nature. Why parabolic in nature? Sorry, this variation is parabolic in nature. So how you can say that it is parabolic? Because the only variable u is basically a function of r and it is dependent on r. Basically u is dependent on r raised to the power of 2. So it is parabolic variation. Okay. It is parabolic variation. So qualitatively and the value of u is equal to 0 when r is equal to r, and you can see that from this particular equation when u will be maximum, when this r will be minimum. And what is the minimum value of physical possible value of r? The minimum value is 0. So u will be equal to u max when value of small r is equal to 0. So and that maximum value is this. Okay. And if we combine these three facts together, what are those three facts? First fact is at r equal to r, it is 0 at for a particular section, okay. On the pi wall it is equal to 0, on the center it is maximum, and the variation is parabolic. So something like this will obtain. Okay, something like this we will obtain. So this is the velocity distribution. Okay. So we have seen the variation of shear stress with r. We have seen the variation of velocity with r. Next is what is the relationship between u and u max? See, u is equal to this, u max equal to this. Okay. So what you can do is, if in the same equation, okay, in this equation, or okay, let us clear the space. Okay. U is equal to minus of 1 by 4 mu del P by del X r square minus r square. Okay. This can be written as U is equal to minus of 1 by 4 mu del P by del X. If I take r square common, then I will get 1 minus r square by r square. Now what is this term? This term is nothing but u max, the maximum velocity which occurs at the center, 1 minus r by r whole square. So this is the relationship between u and u max. So u by u max is equal to 1 minus r by r whole square. Okay. So again, this is a very important equation. See, the main idea is how to derive these equations. Once you have derived the variation of tau versus r and variation of u versus r, rest everything, these equations are manipulations which will make it easier for you to solve problems. Okay. And also it will save you a lot of time if you can remember these equations. Okay. At least the main ones. Okay. Now, next is how to compute the discharge, or how to derive the expression for discharge Q. So, if you again consider that there is a elementary ring, okay, say this is the, now I am taking the cross section of a pipe, okay, and if you consider that, say this is the actual, sorry, yeah, let us say this is the black line represents the actual pipe, okay, pipe cross section. All this time we were looking into the longitudinal profile or longitudinal section of the pipe. Now we have considered the pipe cross section and say this is the pipe center. Okay, let us consider that there is a ring. Okay, there is a ring. So for it, okay, ring, and you want to compute the discharge through this ring. Okay, say the discharge through this ring is dq. Okay, so discharge is equal to what? Area into velocity. Velocity is u. Okay, velocity is u, the expression for which we have already derived. What is the area? What is the area through this pipe? Okay, what will be the area through this pipe? Let us say the distance of this inner ring, the radius for this inner ring is r, and the thickness means this inner circle. Okay, see, for it to be a ring, if I am drawing separately, for it to be a ring, there are two concentric circles. Sorry. There are two concentric circles, right? There are two concentric circles. So this is one circle, and then there is another circle. Okay, such that the center lies here. So there are two concentric circles. Something like this. Okay, the radius of this inner circle is say r, and the thickness of this ring. Okay, the thickness. Let me make it clear by the means of a proper diagram. Yeah, sorry. Yeah, this one is perfect. Say this is a ring. Okay, we are only interested in this much area. This is a ring. We are only interested in this much area, and these are two concentric circles. So this is the center. Say the diameter, the radius of the inner ring is r, and the thickness, which will be same everywhere because these are two concentric circle, is dr. Okay, so building on similar thing, on a similar idea, say this is dr. Okay, this is dr. Now since this thickness dr is very small, what we can do is, see, we need the discharge through this ring only. So if I cut somewhere, okay, if I cut it somewhere and I, look at it, then I'll be getting something like this. Okay, I'll be getting something like this, such that this dimension is dr, and this is, say, approximately the circumference of the inner circle, 2 pi r. So if I open it up, I will be getting approximately a rectangle. Okay, it will not be an exact rectangle. Why not an exact rectangle? Because see, the radius of the outer ring, say I am writing r2, is much, is means will be greater than r. Okay, not much, but it will be definitely greater than r. Okay, that is the radius of the inner ring. But if we consider that the thickness of this ring is very small, that is dr is a elemental length, then approximately r2 and r are same. Okay, and building on this idea, okay, I can consider that the area of this, the area through which the flow takes place across this ring is 2 pi r into dr. So dq is u 2 pi r into dr. But I want the discharge through the entire pipe cross section. So the discharge through the entire pipe cross section is nothing but integration of dq. But from where to where? See, the variable is r. So r will vary from 0 to capital R. So basically discharge is integration from 0 to r u 2 pi r into dr. But that's not all. Now what you have to do is, we have to use the expression for u. So what is u? U we have already seen is equal to u max. Okay, what we have obtained? U is equal to u max into 1 minus r square by r square into 2 pi r into dr. Now here what are the constants? you can bring out the constants outside of the integration. So 2 pi u max will directly come outside the integration, 0 to r 1 minus r square by r square into r dr, or what you can write, 2 pi u max integration from 0 to r minus r cube by r square dr. Okay, or 2 pi u max. Okay, okay, integration of r will be what, r square by 2, and this will be r4 by 4 r square, and integration is from 0 to r, equal to 2 pi u max. Okay, now if you put the limits of integration, it will be r square by 2 minus r 4 by 4 r square minus, if you put 0 here, it will be 0, if you put 0 here, it will be 0, so no need of writing the lower limit of integration. So 2 pi u max, it will be r square by 2 minus r square by 4. So effectively pi u max r square by 4 into 2 is there. So pi u max, pi u max r square by 2. Okay, so this is the pi u max r square by 2. So this is the expression for discharge. So what will be the discharge? Discharge q is equal to pi u max r square by 2. So this is the expression for discharge. Okay, now what is the expression for average velocity c? We have found the expression for instantaneous, okay, velocity. We have found u max, we have found expression for tau, we have found expression for discharge. But what is average velocity for a section? The average velocity at a section is u average q by a. Q is pi u max r square by 2 divided by area. So pi r square. So 1 by pi r square. So it is basically amounts to u max by 2. So u average is half of the maximum velocity. So this is a very important concept. You can get one mark questions in competitive exams also. Okay, so if you remember, it is a very important fact that for a pipe flow, the average velocity is half of the maximum velocity. Okay, this is very important. So I hope it is clear till this point. Is there any doubt? Any doubt? Any doubt? Okay. So there is no doubt, then we will proceed. The last part of this derivation is the derivation of the Hagen-Poiseuille equation. Okay. So Hagen-Poiseuille equation, in order to derive Hagen-Poiseuille equation, we will be using the already derived expression. So we have seen that u average is equal to u max by 2. What is u max? U max is equal to, what is u max? See, if you look carefully, what is U max? Okay, let me do it more fundamentally. U is equal to 1 minus of 1 by 4 mu del P by del X R square minus R square, right? So what will be U max? U max is minus of 1 by 4 mu del P by del X R square. So U average will be, if I use this equation, 1 minus, instead of 4, this it will be 8 because 2 will get multiplied, 8 mu del P by del X R square. Okay. Now what will be minus of del P? Minus of del P will be 8 mu U average by 8 mu U average by R square into delta X. Okay. Now if you consider two locations, okay, if say this is a pipe and you have considered two sections, okay, say section 1 and section 2, such that the pressure here is P1 and pressure here is P2, and say the coordinates or the length with respect to a suitable origin of here is x1 and here is x2, then if you integrate minus del P, if you integrate pressure from P1 to P2, okay, along the right hand side, you will see that all these terms are constant, 8 mu U average by R square for this given set of conditions, except delta X where it will take place. So from integration will be from x1 to x2. Okay. Now there is a negative sign and this will amount to P2 minus P1. Okay, P2 minus P1 with a negative sign. 8 mu U bar by R square, and here it will be x2 minus x1. Now P2 minus P1 is with a negative sign is nothing but minus of P1 minus P2, 8 mu U average by R square. Okay, 8 mu U average by R square into C. What is the figure that we have considered? This is section 1, this is section 2. The x coordinate is x1 for point 1 and x2 for point 2. x2 minus x1 is nothing but the distance between section 2 and section 1, which is say L. Okay. So P1 minus P2 is equal to 8 mu U average by R square into L. Or P1 minus P2 is equal to 8 mu U bar L by R squared. Now if you replace R as D by 2, what will you get? If you replace R with D by 2, then P1 minus P2 will be 32 mu U bar L. R, instead of R square it will be D square. Okay. So this is known as Hagen-Poiseuille equation. Okay. This is known as Hagen-Poiseuille equation. So this much concept was essential for solving the problems related to laminar flow in pipes. Okay. One more important concept that we will be using for solving problems in today's session is friction loss or major head loss through a pipe. Friction loss or major head loss through a pipe is given by HF is equal to FLV square divided by twice GD. So this is known as Darcy-Weisbach friction factor. Okay. One common question is that in some books it is written as 4F, in some books it is only F. Okay, it is a very common confusion. So in order to clear this confusion only, I have taken up this particular concept. See, there are two things. There are two friction factors. Okay, friction factors. One is Fanning's friction factor and the other is Darcy friction factor. Fanning's friction factor, say I am writing CF, and Darcy's friction factor is, say I am writing F. Okay. The relationship between Fanning's friction factor and Darcy's friction factor is F is equal to 4 times of CF. Okay. So those books which are writing 4F instead of F here in Darcy-Weisbach equation, they consider this F to be Fanning's friction factor. Okay. And those books which directly write as FLV square by twice GD, there, okay, you have to understand that F is Darcy's friction factor. So this is a very vital point, and most of the time there is a lot of confusion among the students regarding this 4F and F. Okay, so you have to remember that if it is 4 times of F, then that basically, see, in Darcy-Weisbach friction factor, we have to use Darcy's friction factor, right? So those who use Fanning's friction factor, they multiplied it with 4 to obtain Darcy's friction factor, and those who are not multiplying 4, they are directly actually using Darcy's friction factor. So if in the question it is given to you that you have to use Darcy-Weisbach equation, however the friction factor that is given to you is Fanning's friction factor, then you need to multiply 4 with Fanning's friction factor to obtain Darcy's friction factor, and that you directly use in Darcy-Weisbach equation. However, if it is given to you that it is Darcy's friction factor, you directly use it in Darcy-Weisbach equation without multiplying it with a 4. So that is the only difference. One more important point is Darcy-Weisbach equation for the determination of major head loss or friction loss in pipe is equally valid for both laminar as well as turbulent flow. Okay, it is equally valid for both laminar and turbulent flow. All the equations that we have derived till now were valid only for viscous or laminar flow through pipes. However, this Darcy-Weisbach friction factor equation, this Darcy-Weisbach equation, which is used for the determination of the major head loss in pipes, is valid for both laminar as well as turbulent flow. Okay. And next we have the case of turbulent flow in pipes. Now for turbulent flow in pipes, we'll directly look into the question because we don't have much time left and we need to practice the questions also. So while solving the problems only, we will look into it. So let us open the problem sheet. So this is your first problem. Okay, this is your first problem. Okay. So a fluid of viscosity 8 poise and specific gravity 1.2 is flowing through a circular pipe of diameter 100 mm. The maximum shear stress at the pipe wall is 210 Newton per meter square. The maximum shear stress. You have to find the pressure gradient, the average velocity, that is U average, and the flow Reynolds number, that is RE. Okay, so this is the first problem. So basically what is the situation? The situation is there is a pipe, okay, whose diameter is 100 mm and there is a fluid flowing through that pipe, okay, whose viscosity is 8 poise. If it is 8 poise, then you first of all you tell me whether it is dynamic viscosity or kinematic viscosity. Poise is a CGS unit. Okay, so you first of all see whether it is dynamic or kinematic viscosity depending upon the unit. The specific gravity is given, so the density is not given to you directly, but the specific gravity is given, which is 1.2, and it is a circular pipe. the maximum shear stress at the pipe wall, definitely we have just now seen that shear stress tau is equal to minus of r by 2 del p by del x, and it is maximum when r is equal to capital R. So shear stress is maximum at the pipe wall, and that maximum shear stress value is given to you, which is 210 Newton per meter square. So you have to determine the pressure gradient, you have to determine the average velocity, and you have to determine Reynolds number of flow. Now you do it step by step. Try this problem for some time and then we will look at the solution. Okay, any answers? Let us look at the solution. It is given to you that the viscosity of the fluid is 8 poise. Okay, now if you remember, there are two types of viscosity. Means there are two ways of expressing viscosity. One is dynamic viscosity mu. Okay, other one is kinematic viscosity nu, which is equal to dynamic viscosity divided by the density, mass density rho. Okay, now the SI unit of dynamic viscosity is Newton second per meter square, and for kinematic viscosity it is meter square per second. The CGS unit of dynamic viscosity is poise, and for kinematic viscosity is Stokes. Okay, now in the question it was given to you that it was 8 poise. So if it is 8 poise, then how do you convert this poise to SI unit? Okay, it is given to you that it is 8 poise. So 1 poise is equal to 0.1 Newton second per meter square. So Newton second per meter square. So if you multiply 8 with 0.1, you will be getting this in uh, SI unit. The specific gravity is 1.2. So specific gravity is what? Specific gravity is, say I am writing Sg is equal to density of the fluid that you want to find divided by density of water. So density of water is 1000. See, until and unless given otherwise, you can always choose the density of water as 1000 kg per meter cube. So the specific gravity is 1.2. So the specific gravity of the fluid under consideration for this problem is 1.2 into 1000, which is 1200 kg per meter cube. Diameter of the pipe is 100 millimeter or 0.1 meter, and the maximum shear stress is 210 Newton per meter square. See, the first step that you need to do for this problem is the third part, that is the Reynolds number of the flow. Okay, that is the Reynolds number of the flow. Why? Because if you are not sure whether the flow, see from the question, it is not at all clear whether the flow is laminar or turbulent, because the Reynolds number is not directly given to you. So if you want to use the equations that we have derived in today's lecture session, you need to make sure that the flow is laminar. Okay, if the flow is not laminar, you cannot apply those equations. So that's why you first of all need to obtain the Reynolds number. Reynolds number is rho v d by mu. But the question is, v is not given to us. Okay, v is not given to us. So what you can do? V is not given to you. Okay, V is not given to you. So what you can do? Just think carefully. If V is not given to you, for Reynolds number, you need U average. Okay, for Reynolds number, you need U average. Okay. So for U average, you have seen that it is U max by 2. Okay. So you can assume that the flow is laminar. Okay. Once you have assumed that the flow is laminar, from the given data, you can find the value of U average, and then you can find the value of Reynolds number if it satisfies. Okay, if it satisfies your assumption, then whatever value you have assumed is correct. Otherwise, with that new value, you just proceed. Okay, with the trial and error procedure. For example, for this problem, if you need U average, you need the value of del P by del X, which is also not given to you. So that is the first part, the pressure gradient. Now, if you assume that the flow is laminar, then how you can obtain pressure gradient? See, tau max is equal to minus of R by 2 del P by del X. Okay. Tau max is given to you, which is 210 Newton per meter square. R is given to you because the diameter is given to you. You know R, so you can find del P by del X. Sorry, you can find del P by del X. Okay. So that is the first part. So del P by del X is approximately 8400 Newton per meter square. Okay, this is the first part. Once you know del P by del X, U average is equal to half of U max. For obtaining U max, you need the value of del P by del X, which you have already calculated. So from this, the value of the average velocity came out to be 3.28 meter per second. Okay. Next, with this value of average velocity, you calculate the Reynolds number, which is 492. So if it is 492, it is much below 2000. So the assumption that we have considered is that the flow is laminar. So whenever you are solving a problem on pipe flow, you make sure that whether in the question it is given that or not the flow is in laminar range or turbulent range. Okay. If nothing has been mentioned, then you assume that it is in laminar range and then you do the questions. But see, this is a very mm, crude type of problem. In actual, see, whenever you sit for some competitive exams or maybe your college or university examinations, the questions will be well prepared, and there this kind of like seldom you have to make assumptions of this kind. Okay, but again, I have intentionally chosen this question to make you realize the importance. Okay, whenever you are solving problem, blindly applying the formula is not correct. You need to understand in under what situation you can apply this equation. If suppose you are not sure of the situation, how you can proceed. Okay, so that was the purpose of this first question. Again, calculation wise, it is a very simple question. You can do it. Let us try the second problem. In a pipe of 300 mm diameter, the maximum flow velocity is found to be 2 meter per second. If the flow in the pipe is laminar, find the average velocity and the radius at which it occurs and the velocity at 50 mm from the wall of the pipe. Please read the screen for 1 minute and try to visualize the problem. So the problem is there is a circular pipe whose diameter is 300 millimeter. Okay. Maximum velocity 2 meter per second. Now see, here you can see that it is given to you that the flow in the pipe is laminar. So now you can like very easily apply all the equations that we have derived today. So you have to find the average velocity. Okay, U average. And if U average will definitely have some magnitude. So at what distance from the pipe center, that at what value of R this U average occurs. That is the first part. And what is the second part? The second part is the you have to determine the velocity at a point which lies at a distance of 50 mm from the pipe wall. That is at y equal to 50 mm from the at y equal to 50 mm you have to find the velocity. Okay. So this is a very simple problem. If you have understood today's session till now, then it should not take much time. Please try this problem and then we'll look into the solution. So it is given to you that diameter of the pipe is 300 millimeter. Then what will be the radius? 150 millimeter or 150 by 1000 meter, which is 0.15 meter. Okay, this is the radius. U max is equal to 2 meter per second. Flow is laminar. And what is the fluid? Nothing has been mentioned. Now the first part is you have to find the U average. So U average, we have seen that U average by U max is equal to half. So U average is equal to U max by 2. U max is 2, so it is 1 meter per second. Okay, this is the first part, 1 meter per second. The second part means of the first sub problem is that the radius at which it occurs. Okay, the radius at which it occurs. See, nothing has been mentioned about the fluid, and the value of the viscosity is also not given to you. So you need to use the equations very carefully that you have derived. Okay, you need to use the equations very carefully. So what you can do is, see, we have seen that, sorry, U is equal to, excuse me, okay, U is equal to minus 1 by 4 mu del P by del X 1 minus R square by R square. Okay, or we have also seen that U is equal to, sorry, this is not the equation that we have derived. U is equal to 1 minus 4 mu del P by del X R square minus R square. So U is equal to minus of 1 by 4 mu del P del X R square 1 minus R square by R square. Okay, U is equal to U max 1 minus R square by R square. Okay, now see, you have to determine the value of R where U is equal to U average. So if you substitute U average here, you will be getting this equation U max 1 minus R square by R square. Okay, so value of U average we have already obtained 1. Value of U max is given to you, which is 2. 1 minus R is your unknown, and capital R is 0.15. So 0.15 square. Okay. So solve this equation and you find the value of R. So the value of R is approximately 106 millimeter or 0.106 meter. The second part is the velocity at a distance 50 mm from the pipe wall. Okay, so please try this one. So what is the second part? Second part is, say this is your pipe. You have to find the velocity at a distance of 50 mm from the 50 mm from the pipe wall. So we have already seen what is the relationship between Y and R. What is this relation? Y is equal to R minus R. Okay. So if Y is equal to 50 mm, the value of R is known to you. You can find what will be the value of small r. So small r will be basically R minus Y. Okay, R minus 50 or R minus Y. So R is basically 150 minus 50. So 100 mm. So at R equal to 100 mm, you need to find what is the velocity. So how you can find this? Very easily again, U is equal to U max 1 minus R square by R square. Okay, so the value of R is 100 mm or 0.1 meter. So if you use that, it is approximately 1.11 meter per second. Okay. So I hope this problem is clear. Any doubt? Again, this was a very simple problem. Okay. Now this particular problem is from the chapter on turbulent flow. So it is given that the pipe is smooth. We'll come to that. But before discussing about the turbulent flow part, I would like all of you to calculate for the given situation. The diameter of the pipe is given 0.5 meter, length is 1000 meter. It is given that the flowing fluid is water, so you know the density. The discharge is given 0.05 meter cube per second. The kinematic viscosity is given as 0.02 Stokes. You first of all find what is the Reynolds number. I'm giving you 5 minutes of time. You find what is the Reynolds number, and if possible you also find the head loss due to friction, because we have already discussed the Darcy's equation. But again, if you are, at least find the Reynolds number. Okay, at least find the Reynolds number. You calculate the Reynolds number, that is rho v d by mu. I'm giving you 5 minutes of time and then we'll discuss in the solution. Okay. Okay, so what will be Reynolds number? Rho V D by mu. In the question it is given that it is water, so rho is 1000 kg per meter cube. The diameter of the pipe is given to you in the question, which is 0.5 meter. So it is a big diameter pipe. The value of mu is not directly given, but the value of nu is given. The kinematic viscosity is 0.02 Stokes, that is in CGS unit. So 0.02 Stokes to meter square per second, 10 to the power minus 4 meter square per second, and v is nothing but the average velocity. So average velocity is what? Average velocity is discharge by area. Discharge is given to you. Discharge is 0.05 meter cube per second divided by area is pi d square by 4. So see, in order to determine Reynolds number, all the parameters or all the variables are known to you. So you just calculate v, you calculate mu, and then you put it in the equation for Reynolds number and tell me what is the value of Reynolds number. So Reynolds number is, see, with the same calculations, 6.365 into 10 to the power 4. So this is much higher than 4000. So that's why the flow is turbulent. So that is the first step. You have to determine Reynolds number. Now once it is, you have determined what it is turbulent flow. So now you will jump to the actual problem. Head loss due to friction. So head loss due to friction is given by Darcy-Weisbach equation. So Darcy-Weisbach equation, as I have already mentioned, is valid for both laminar as well as turbulent flow. So HF is equal to FLV square by twice GD, where this F is Darcy's friction factor. Okay. Or if Fanning's friction factor is given to you, then you need to use 4 times of CF. But the problem is, in the question, F is not given to you, F or CF, nothing is given to you. So how you can determine? You can definitely determine it, because how you can determine it? There are many equations available which relates this friction factor with Reynolds number. Okay. As well as pipe roughness. So since it is turbulent flow for a smooth pipe, you must have seen this equation. The Darcy's friction factor, see this is actually Fanning's friction factor here, CF 0.0791 Re raised to the power of 1 by 4. So from here the value of Fanning's friction factor is 0.005 approximately. Since it is Fanning's friction factor, in order to make it Darcy's friction factor, you need to multiply this with 4. Everything else is known to you. Average velocity is known, length is known, diameter is known, 2g. See, the length of the pipe is given in the question. 1000 meter, the stretch of interest. Okay. So the head loss due to friction is around 0.1316 meter. So around 0.13 meters. Wall shear stress. So again, this is in terms of Fanning's friction factor, that is CF rho v square by 2, where v is nothing but the average velocity. So you can find the wall shear stress, that is the shear stress at the pipe boundary, that is tau 0. The center line velocity, see, in case of turbulent flow, if you have gone through the lectures carefully, then you must have seen that, see, in case of laminar flow, the velocity variation was, parabolic. Okay, the velocity variation was parabolic. However, in case of turbulent flow, it follows a logarithmic distribution. So it is this distribution. This is coming for smooth pipe. Now what is a smooth pipe? When the roughness lies within laminar sublayer, we call it a smooth pipe. So for this, the relation is known to you. So from there you can directly calculate the value of U max 0.303. See, the analysis is more or less similar to that of the laminar flow, only the equations are different. Why these are different? Because in case of turbulent flow, in order to determine this velocity variation, Bosenick's hypothesis, then Prandtl's mixing length theory, all these additional theories which are relevant for turbulent flow but which were not there in case of linear flow are applied, and that's why you have obtained a logarithmic velocity distribution. Now here, what is this UF? UF is the shear velocity, or in some books it will be represented by U star. So it is the square root of the ratio of the wall shear stress divided by the density. So it is basically, it is not a physical velocity, but it represents a quantity whose unit is that of the velocity. So that's why it is known as shear velocity. So if you substitute all these values, you will be getting the values of U max, okay, which is 0.303 meter per second. Then thickness of the laminar sublayer for a smooth pipe, 11.6 nu by U star or UF. So everything is known to you. It is approximately 1.826 mm. It means that the average height of the roughness parameters on the pipe, okay, element is less than 1.826 millimeters. So it lies well within this layer. Okay. So I hope this problem is clear. Any doubt? You can ask me, or you can even write in the message box. So if there are no doubts, then I hope everything is clear and we can move to the next problem. You have to find the distance from the pipe wall at which the local velocity is equal to the average velocity. Okay. For any general pipe, a circular pipe, you have to find the distance from the pipe wall, that is y, at which the local velocity, that is u, is equal to the average velocity. Okay. But for turbulent flow in pipes, we have solved a similar problem, numerical problem, in case of laminar flow. Now you have to do the same for turbulent flow in pipes. You have to find the distance y at which the local velocity is equal to the average velocity. Okay, so please try this problem for some time and then we'll look at the solution. And this is basically the last problem for today's session. Any updates? Okay. So let us see. The local velocity at a point u should be equal to u average. Now this is a very famous relation for turbulent flow in pipes, which you must have seen. U minus u average by u star is equal to 5.75 log to the base 10 of y by r plus 3.75. Okay. Now if u and u average are same, then this particular term will become 0. Okay, so if this particular terms become 0, 5.75 log to the base 10 y by r is equal to minus of 3.75. And finally, if you bring 5.75 to the other side, it is log to the base 10 y by r is equal to minus of 0.652. Now 10 to the power of minus 0.652 is equal to y by r. So whatever is the value is 0.223. So y equal to 0.223 times of r. So this is again a very important question. uh, in terms of descriptive question, you can get it like a derivation, or if you are expecting this question in case of competitive examinations, then they may give you some problem which might involve direct application of this term, that is y is equal to 0.223 times of r for general turbulent flow case in pipes. So since we have limited contact period hours, I was able to discuss in details the equations for laminar flow in pipes or viscous for a viscous fluid. However, we have seen two problems related to turbulent flow in pipes. The time constraints has forced like that the time constraints, excuse me, the time limitation has forced us to skip the chapters or derivations related to turbulent flow in pipes. So if you have any doubts, you can take up the doubts during the next session, or we will discuss other problems which are relevant to the contents of week 4 in the next session. And you can I am repeatedly telling you that you need to follow the video lectures very carefully, because all these derivations are given in details and discussed in details in the video lectures. And in case of any doubts, you can ask, or we can wind up today's session. I'm giving you few minutes to summarize whatever we have learned today, and in case of any doubt, you can ask me. I'm there. Any doubts? You can even write in the message box your doubts. Okay, if there are no doubts, then I think we can wind up today. Thank you very much. You can all exit the meeting. Stop here. Thank you.